Hello, welcome to the sixth session of this course. So today we'll also describe Cauchy inequality. Actually, the angle between two complex numbers. So let's start. So last time we did this one, Cauchy inequality. So this one last time we did, which was inner product ZW, inner product with respect to R, modulus less or equal to mod Z mod W for all ZW in C. So, and this actually, from this one can get the concept of angle between two complex numbers. Let's look at that. So this implies mod of ZWR by mod Z mod W is less than 1, which implies ZW R inner product ZW over R mod Z mod W. This lives in the interval -1 to +1. Alright. So now once it is in this form, you can actually, this implies there exists a theta, a unique theta in 0 to 2 pi, such that cos theta is ZWR by mod Z mod W. So this theta, so if you have this picture, so let's look at the picture, y-axis. So if let's say this is the point Z and this is the point W. So you draw a vector. Since we are looking at over R, you can write a vector like this. Yeah, so this is W and this angle is theta, such that cos theta is this. So you have angle, the concept of angle. And of course, this matches with the polar coordinates perfectly well when you look at the angle between x-axis and the vector. We'll come to that, but not now. Now we look at, let's go back to look at more carefully this one, ZW, which is ZWR. Alright, we have the real part to be the inner product, which gives the angle. Let's look at more carefully again, putting Z equal to x plus iy, W equal to u plus iv, and here x plus iy, u minus iv. So this gives xu plus yv plus yu minus xv. We look at the imaginary part now. Alright, this one. But so define omega ZW to be minus of imaginary part of this ZW, which is nothing but xv minus uy. Alright, xv minus uy. Well, this also have nice interpretation. So this is also important. So look at now the relation between real part and imaginary part. So what is the relation? So real part which was ZWR. Well, let's look at the other way around. We look at first imaginary part. It's omega, and we put Z, IW, which is imaginary part, and there is a minus sign Z, IW bar, which is imaginary part of Z. There is a minus comma coming out, IZW bar. Alright, so now this is imaginary part of I x plus IY J U minus IV. Right? So now see there is a multiplication I. So here you have already calculated, and if you multiply by I, imaginary part comes to be this one. Right? Yeah. So which is minus imaginary part of this one, which is this one. Yeah. So here okay, so I made a mistake here. See here minus I, minus is coming out, so it will be plus. So it will be plus, yes, it will be plus. So imaginary part of this one, which is imaginary part of, we multiply I with this, so I times xu plus yv minus I yu minus xv. So imaginary part comes to be this one, xq plus yv, which is ZW R. So you see what we get? We got this equal to ZW this. Right? This equality we got. Yeah. So this is nice. And you see, if you look at this carefully, omega, this is nothing but dx which dy acting on z comma w, viewing z and w as a vector in R2. And this is, if you know differential form a little bit, then you can surely note W to be this one. And this is the volume form in R2. So this is really important. Yeah, okay. So if you don't know differential form, don't worry, you know this remark. But what is the point is that imaginary part is also quite important. It's not that it is not important. Alright? So let me put another a question in linear algebra in this context. Alright, so So I will put the question here and then we'll try to answer that side. Suppose V is a vector space over real number. Okay? Any vector space. When can we visualize or view V as a vector space over C? Alright? You have a vector space over R. When can you view it as vector space over C? Of course, R2 you can visualize that vector space over C because it's the C, it's complex number. Right? R4 you can do the same thing. You can view it as C2. So what about general vector space? Well, the answer is as follows. So this is a question. Linear algebra. Answer: when we have a map or invertible map J V to V such that J square is minus identity. If there is a map such that it holds, then we have y. Here it is. So if once we have assume we have one, then define J alpha plus I beta, a complex number, times the vector V. V is coming from the vector space V. We did not have scalar multiplication when the scalar coming from complex number, which we want to incorporate. So this one, alpha times V plus beta, so this is the definition, times JV. Right? We can define this way, check. 2 gives V a vector space structure over C. The J map in our case, in case of R2, this J map is just I map. What is I? I is, if you look at from R2 to R2, it takes I of xy is minus y comma x. Just I of j is I times x plus iy, which is minus y plus ix. This is it. This is what allows you to see R2 as a vector space over C, which is C. Alright? So the generalization of this is this one. So there is quite a bit of generalization and far-reaching generalizations are there. And so once you have this J, then you have this two as well. So this one will be actually generalized to ZW by R ZW. Well, here ZW is a vector space, so it's coming from vector space, so let's take it u comma v. So write it u comma v. U v coming from vector space V. Alright. So there's a lot of generalization about, and this is the beginning point of complex geometry. Alright. Thank you very much. We'll see you later.